Assalamu alaikum and a very good day. My name is Muhammad Izzan bin Abdul Samad, metric number P112520002. Now I will be presenting my research proposal defense for my topic, which is neural network-based stability guaranteed control for non-linear electrohydraulic systems. This presentation is separated into 8 main sections, which are shown here, which will be covered in each slide after this. The reason I chose electrohydraulic systems is because it is considered to be the backbone in heavy industries due to its high force-to-weight ratio, as well as the high demand in the Industry 4.0 transitions, as well as addressing the issues of energy and cost savings. This is also in line with the alignment of the SDG 9 goal by the United Nations and its high demand in the electrohydraulic market or hydraulic market shown here in this chart, and in terms of the Asian Pacific hydraulic market shown in this chart here. Here are some of the many engineering applications of electrohydraulic systems that can be found in our daily lives. The problem statements that have been identified in terms of technical gaps are the coupled physical nonlinearities in electrohydraulic systems, which include friction, fluid compressibility, and valve dead zones. And in terms of conventional controller limitations, fixed PIDs cannot adapt to parameter variations, sliding mode controllers introduces chattering, which affects actuator performance, and in terms of model predictive controllers, it requires an accurate and high computational complexity for real-time implementation. And the problem statements identified in safety gaps are the lack of formal stability guarantees, which is the limited stability analysis through Lyapunov-based stability proofs, the risk under uncertainties of parameter variations, and idealized assumptions which may not hold in practical applications, as well as the simulation to real development gap, which addresses the real-time implementation of the controllers, the hardware integration of the controllers, as well as the already available yet limited experimental validation. The research scope and boundaries of this research will be focused to the physical test rig platform provided, the uncertainty parameters which will be measured, the intelligent architecture of the controller, the development ecosystem, in this case will be MATLAB or Simulink, as well as the hardware interface that is provided. And the exclusions of this research is no reinforcement learning, no multi-access networks, and no embedded field programmable gate array, or FPGA. Among the questions asked throughout this research is how can the controller and structure can be designed and trained to capture the nonlinearities under various profiles? How can this structure be mathematically proven via Lyapunov theory or stability theory, and whether this neural network can minimize tracking delay and suppress the chattering on the physical devices. And in terms of the hypothesis, among the objectives of this research is to develop the data-driven neural network dynamic model, to design the control framework which is mathematically bounded to the approximation errors and system stability, and most importantly, to experimentally validate the controller using the physical test rig and compare it with the standard PID and classical SMC. Among the physical gaps identified throughout the literature review are the slipstick friction by this study, the internal fluid leakage carried out by this study, the bulk modulus variations by this study, focusing on shifts in oil stiffness, and of course, the most important, valve dead zones by this study. Based on this literature review, the conventional PID lacks the adaptability towards parameter changes. The classical SMC models introduces chattering to the systems. The model predictive controller contains mismatches, and the adaptive robust controller requires handcrafted analytical models to carry out its function. And this is the controller comparison from the literature review based on the types of controller methodologies, their core strengths, and their limitations as shown here. Based on the literature review, here is the K-chart that I have developed, which addresses the research gap, which shows that there is no unified framework which integrates MLP-based learning, Lyapunov stability guarantee, adaptive robust control, and real-time physical validation. This is the overall methodology flowchart shown here, which is separated into 6 unique phases, which cover the 3 main objectives. To fulfill Objective 1, first we do the literature review and initial system identification to identify the limitations of control strategies, to establish design constraints and research gaps, and then after that we develop the mathematical system modeling, which is then validated to ensure that it is correct, and if it isn't, it is refined and corrected before moving to data-driven modeling. To fulfill Objective 2, first we carry out the data collection, and then we develop, train, and optimize a neural network model. Then after that, from this neural network model, we design and create the controller, which will then be run through Lyapunov stability analysis. If the stability criteria has not been met, we either redesigned the neural network model or we redesign the controller itself before going to the next phase. And finally, to fulfill Objective 3, we carry out a simulation validation to validate the created framework under nominal conditions and an experimental validation to assure the real-time functionality as well as assess the capabilities in terms of tracking accuracy, robustness against uncertainties, and external disturbance rejection. Among the expected outcomes of this research is a validated model with high prediction accuracy, a stability guaranteed controller proven through Lyapunov theory, and a validated controller with improved tracking and robustness. This is the overall Gantt chart and timeline of our entire research, which covers the targeted span of 3 years, or, in more accurate terms, 12 quarters. Among the contributions of this research is the hybrid control architecture produced, the theoretical safety certificate, which is proven by the Lyapunov stability-based proof, the dynamic uncertainty estimation using online learning, and a framework that bridges the simulation to hardware gap. And in terms of the impacts of this research is heavy industry reliability, energy and wear reduction, in particular mechanical wear, supporting the System Development Goal 9, and guaranteed operational safety in fail-safe operations. In conclusion, this research addresses the absence of formal stability guarantees in standard intelligent control architectures. This framework aims to deliver an efficient controller that enhances operational reliability and energy efficiency in high-power industrial automation systems, which supports the Sustainable Development Goal 9 by the United Nations. Here are some of the many references which is used throughout this research. And here are some more additional references that is used throughout this research. And here are the corresponding links to the images used throughout this presentation. That is all from me. Thank you.